Okay, so it is 3:30. We can go ahead and get started. Yeah, how's everyone doing? I do know that there in my getting to know you survey, there was about maybe 25% of you that were like interested in raising your hands and saying things out loud. So I would say if you're one of those people, you can definitely go for it. I do think we're at the point in this class where yeah, the people that want to come are coming. So I think, it probably, if you wanted to be one of those people that raised your hands to answer a question rather than just using the chat, if you felt like that would be kind of a way to, keep the class a little bit more engaging, yeah, I would definitely say, go for it. But yeah, anyways, unfortunately, like teaching online it's not my top choice, if you will. I'm sure it's not a lot of people's top choice, but yeah, these synchronous lectures, they're meant to be for you guys. So if you have any suggestions about how we might be able to get more out, of the experience, definitely feel free to let me know. So yeah, cool. So what we have coming up, next homework assignment that is due on Friday, as always. I will be resuming my typical office hours. Thursday, or excuse me, just on Fridays. So if you have any questions, feel free to let me know. And then, yeah, what we're going to be doing today is finishing up with Unit 6, which is cool because basically at this point we'll have all the information that we will need, or basically all the algorithms that we will need in order to assess if a given data set that you're interested in is indeed clusterable. And you can therefore use it for your final project. So I'll be hopefully releasing specifications for that final project within the next few weeks. And like I mentioned, you can choose your own data set. You can use the backup data set if you'd like. But yeah, start thinking about data sets that you find interesting and perhaps how we might explore some of the analyses that we're learning in this class to unlock hidden insights about that data set. So if you have any questions about a particular data set that you like, definitely feel free to let me know by office hours. We're here to help. So yeah, any questions before we get started? All right, cool. So, what we wrapped up with last Thursday was basically talking about three analog algorithms, which are very similar to algorithms that we had discussed that are able to cluster purely numerical data sets. We basically took three of those techniques and modified them slightly in order to allow us to cluster purely categorical variable data sets. So basically in today's class, we're going to be doing the exact same thing. We're going to be taking those three types of clustering algorithms, and we're going to be slightly modifying them such that now we're going to be able to perform the same basic analysis to data sets that are now comprised of a mixture of both numerical and categorical variables data sets here. So for instance, we'd like to take our actual bank client data set, which has two numerical variables and a couple of categorical variables, and again, cluster those bank clients. And yeah, use our insights to learn more about what types of groups basically the clients break down into. So what we saw with the purely categorical data set was that we ended up seeing this socioeconomic status to the clusters that were essentially formed. So the question is, if we use the actual data set, right? So if we actually use age, which has not been bucketed into a categorical variable. If we use, for instance, bank balance, the question is, are we going to see that same socioeconomic status breakdown? Or perhaps do there exist other types of clusters or clustering relationships when we include the full data set? So that's something that we might want to know. So the question is, first, how do we evaluate if this mixed data type data set is in fact clusterable? So what we can do is we can go back to our modified TS&E algorithm that we discussed, right? And so we discussed that rather than providing a purely numerical tabular data set as the input into the TS&E algorithm, and then the TS&E algorithm initially calculates the Euclidean distance between those observations as a means of calculating the TS&E distance. So basically, we discussed that when we're, dealing with a purely categorical data set, what we can do instead is we can create our own distance matrix of the original data set, which was purely categorical. So for instance, we supplied the Hamming distance matrix from our purely categorical data set. And then we used that Hamming distance matrix instead to measure the initial distance between 2 points in the data set, and then use that to calculate the TS&E distance, which uses the Gaussian curve. So we are going to talk about how we might do the same thing with a data set that is mixed, or basically has numerical and categorical variables. But rather than using the Hamming distance, we want to talk about a distance metric that allows for us to measure the distance between two observations that are of mixed data types. So one way that we could go about doing that is by using what we call Gowers distance. For instance, if we want to measure the distance between two observations, xi and xi prime, where we know that some of our attributes are numerical and some are categorical, then we can use the following Gowers distance calculation. So we still have this delta function, which we've seen in the past, in which we are now going to be summing over all of the n attributes in the data set. However, in this case, the delta function is going to be defined differently based on whether we're talking about a categorical or a numerical attribute. So if the jth attribute that we are considering is categorical, then the delta between the two corresponding observations, or two corresponding attributes of those two observations, is going to be one in which if those two attributes are the same, then the delta function returns 0. If those two attributes are different, then the delta function returns a 1. Or in other words, the delta function for those two attributes simply just represents the Hamming distance between two categorical attributes. Okay. On the other hand, if the two attributes, or if the attribute that you are considering is numerical, then this delta function represents, one second, what this represents is the absolute value of the difference between those two corresponding numerical attribute values. And we then normalize that absolute value difference by the corresponding range of that particular attribute, or jth attribute here. In other words, what this delta value represents is the normalized Manhattan distance with the L1 norm for that jth attribute. Okay, so basically we sum each of these delta values and then we divide by the total number of attributes in the data set, and that represents our Gowers distance. Okay, so for instance, if we wanted to, let's just say, calculate Gowers distance between these two observations here, what we could do is calculate the absolute value of the difference between 3 and 1. And then we divide by the range of the number of stat class taken. So that's 20 minus 1, so a range of 19. Okay. And then we would add the absolute value of the difference between the ages of 28 and 24. And then we divide by the range of the age. This would be 28 minus 19. Okay. And so the two education levels for these two observations are different. So we would add a 1 corresponding to the Hamming distance. And the type of home for these two people is the same. So we would add a 0. Okay. And so there are 4 attributes in this data set. So we would divide by 4. Okay. So that comes out to a Hamming distance of 0.387. All right. Any questions on that? All right. So naturally, if two observations are exactly the same, then basically you're going to get a 0 in the numerator here, and you're going to get a 0 here. If two observations are exactly the same, then the Gowers distance naturally would be 0. And on the other hand, we want to think about what the maximum Gowers distance that we might end up getting could be. So the highest possible Gowers distance value that you could get between any two observations in a data set is going to be 1. And that would end up happening in the scenario in which every categorical attribute value disagree, and every two numerical attribute values are the two furthest away values in the data set. Write that out a little bit better. Okay, so this serves as a proper, or this basically mirrors what we might expect for a given distance metric. So basically, the more similar two observations are, the smaller that distance value is. And so what we can do is create a Gowers distance matrix in which we calculate the Gowers distance between every pair of observations in this mixed data types data set. And then we can basically use that Gowers distance matrix as our input into the TSNE algorithm instead. Okay, so we'll do that in a second. Any questions on that? Okay, so let's go ahead and do that for our bank client data set. Okay, so this is our data frame of mixed data types. And so unfortunately, the Gowers distance matrix function doesn't come with scikit-learn, so you will have to run this pip install Gower package here. And you can, once you've done that, you can install the Gower package and use the Gower matrix function on your mixed data types data set. And so what that does is it creates a square form distance matrix, which is good. This is basically the input that we need for the TSNE function. So it's not one of those flattened distance matrices. It's, of the right format. And so just like we saw when using the Hamming distance matrix as our input for the TSNE function, we can use that pre-computed distance matrix as our input here. And the only thing that we would want to change is we would want to let the TSNE function know that, hey, we're using our own pre-computed distance matrix. So basically, don't assume that this input is purely just a set of numerical variables that you should use the Euclidean distance on. Okay, so when it comes to interpreting those TSNE plots that we end up getting, we end up using the same protocol for the most part, as we've seen before. So it's always a good idea to try out multiple random states, as well as multiple perplexity values going from the lower bound range of 5 all the way up to the upper bound value of 50. And again, these are the range of perplexity values that tend to give us the most insightful results. Okay. And so what we end up seeing here, and we see this, usually we see this, but not always, that our lowest perplexity value really gives us no evidence yet of any, significant clustering structure. But as we increase that perplexity value in this scenario, we do end up seeing evidence of a clustering structure in the data set. So we do end up seeing some not super well separated, but to some extent separated. So not well separated clusters in these t-SNE plots. And we see this across multiple perplexity values. And generally speaking, it would be a good idea to try this across multiple random states as well. But in the interest of time, we only tried out one random state. So we see a few not well separated clusters. So for instance, we might suggest perhaps that maybe this is, one main cluster that exists in the data set. Maybe this is, evidence of another main cluster that might exist in the data set. But within each of these main clusters, right, we can see some further separations or smaller separations that exist. So this might be an indication that there is some evidence of subclusters that exist within the larger main clusters. Okay, it can also give us a sense as to, maybe one of these, main clusters has more observations than the other. Okay, and so what we can see with our eyes in these t-SNE plots is that, these clusters are at the very least not, or excuse me, at the very least they are convex in shape. But again, given that we're dealing with a data set that has categorical variables, it becomes a little bit less intuitive as to what a shape of a categorical variable set of observations might in fact mean. So just like we saw with the Hamming, just like we saw with t-SNE plots generated with a Hamming distance matrix, it doesn't usually make sense to make a lot of shape interpretations when that t-SNE plot is generated with a Gowers distance matrix instead. So these might be our interpretations that we might make here. Okay. So this is how we can use the Gowers distance matrix to create a t-SNE plot for a mixed data types data set. Any questions on that? Okay. So just like we saw with a categorical data set, we might also, so after evaluating whether or not there is a clustering structure in the data set, we might be interested in using or designing a partition-based clustering algorithm to create a single clustering of this data set. So just like we saw with, when we introduced the k-modes clustering algorithm. So when we introduced the k-modes clustering algorithm, we basically just used the same, general structure of k-means, and we modified two things, right? So we modified what the prototype was that we were using, and we ended up using the distance or modifying the distance metric as well. So in order to create a mixed data type analog based on this Lloyd's algorithm or the k-means clustering algorithm, we're going to introduce another prototype-based clustering algorithm. So this is going to be called k-prototypes. And so what we're going to see is that the structure, again, is very much the same as k-means. The only main difference is our prototype is, rather than being a mean, it's going to be a mixture of means and modes. So we're going to use the mean for the numerical attributes. We're going to use the mode for the categorical attributes. Okay, so that prototype that we just defined here, that's going to be our centroid that we're going to use in the Lloyd's algorithm that we've been using before. And then the distance metric And again, as we've seen for all of these prototype-based clustering algorithms, if we're changing up the prototype, we need to make sure that we're using the right distance metric such that the algorithm is guaranteed to converge to a local minimum of the corresponding optimization problem that we're trying to minimize. So we're going to be careful about what distance metric that we're going to use. So this distance metric is going to be a weighted combination of the Euclidean, or excuse me, the squared Euclidean distance for the numerical variables and the Hamming distance for the categorical variables. Okay. Questions on that? So let's actually get into the nitty-gritty of how we actually would use the K-prototypes algorithm. So, like we said, K-prototypes is very similar to the K-means clustering algorithm. So in K-means, our input was a numerical data set. And so one of our inputs into the K-prototypes clustering algorithm is going to be our mixed data types data set, where it's assumed that a certain subset of our attributes are numerical and a certain subset of my attributes are categorical. Okay. And also, just like in K-means, where we need to pre-specify the number of clusters that we're looking for, we also need to pre-specify the number of clusters that we're looking for here in K-prototypes. And finally, so one modification to the existing prototype-based clustering algorithms that we've seen before is that we're introducing this additional weighting parameter that we need to pre-specify as well. So what this weighting parameter is going to represent is how much or to what extent we should consider the categorical variables in our distance function that we're going to end up defining in just a second. Okay. And so just like in the K-means clustering algorithm, we have some sort of optimization problem that we are trying to minimize. So in other words, we're trying to come up with the optimal clustering that minimizes the inertia of the data set or in the given clustering. So in other words, trying to come up with the optimal clustering that minimizes the squared Euclidean distance of all observations to their cluster centroid CK. And so similarly, the K-prototypes clustering algorithm is also based on a optimization problem in which we are trying to minimize the distance also between each observation and the centroid or the prototype of the given cluster that it was assigned to. But now in this case, in the case of K-prototypes, like we mentioned, the distance function that we're going to end up using is a combination of the squared Euclidean distance between each of our numerical attribute observations and the centroid, or the corresponding centroid attribute of the cluster that it was assigned to. And then for the categorical variables, we're using the Hamming distance. Okay, so that is, we count up the number of disagreements between the categorical attribute values in the data set, between the given observation and the centroid of the cluster that it was assigned to. And then basically we can see here that we incorporate this weighting parameter gamma on the Hamming distance function. So in other words, the higher that gamma value is, the more the categorical variables are going to be considered in the distance function. Okay. Questions on that? So, like we mentioned with all of these other K-prototype-based optimization problems, unfortunately, there does not exist or at the very moment, we don't know of a polynomial time algorithm, or in other words, a fast algorithm, which will be able to find the global minimum to this optimization problem. So what we do instead is we introduce a heuristic optimization problem in which when we select the right distance function, we can guarantee that the algorithm, at the very least, will converge to a local minimum of that corresponding optimization problem. Okay, so the structure of k-means and k-prototypes is going to be exactly the same, right? So we have this centroid initialization step, and then we have this partition update step. We have this prototype or centroid update step, and we keep iterating through the partition or the clustering update step and the prototype update step until some sort of stopping criterion is met. So we have this centroid or prototype in our case, initialization step in k-prototypes. So in k-means, we basically simply just randomly selected values between the minimum and maximum, or basically within the range of the corresponding numerical attributes. So basically our prototype or our centroid initialization step for k-prototypes is going to be that combination of how we initialized the centroids for k-means and k-modes. So in other words, for the categorical attributes, we might simply just randomly select a set of values from each of the categorical variables as our initial prototypes. So maybe I might randomly select masters for prototype 1. I might randomly select bachelors for prototype 2. And similarly, I might randomly select apartment for prototype 1 and house for prototype 2. Okay, and then when randomly initializing the number of stats classes taken, I might simply just randomly select an observation between 1 and 20. So I might select like 7 for prototype 1 and maybe 10 for prototype 2. And then finally, if I want to randomly initialize a age value for my 2 prototypes, I might randomly select 2 values between 19 and 28. So I might select randomly 20 and 23, for instance. Okay. All right. And so my prototype calculation, my prototype or my centroid update step is basically going to be a combination of my centroid update step for k-means and k-modes. So for the numerical attributes, my new centroid is simply just going to be the mean of all of those corresponding attributes. And for the categorical attributes, my corresponding new prototype is going to be simply just the mode of each of the corresponding attributes. Okay. So for instance, the prototype of, let's just say this cluster here is going to be simply just the average of each of the number of stats classes taken. Okay. And the age of my new prototype is simply just going to be the average of the ages. So that's this. Okay. And the mode, my highest educational level prototype value is simply just going to be the mode of the highest educational level values here. So in this particular scenario, we can see that we would, be in a tiebreaker scenario because basically every single one of these values is the mode, right? So we'd need to come up with some sort of tiebreaker rule. So let's just say I'm going to pick the value that corresponds to the lowest object index. So in our case, that would be like PhD. And my mode of the type of home is going to be the apartment. So this is the most commonly appearing type of home. Okay. All right. Questions on that? Okay. So the new prototype is simply just a combination of the way that you would recalculate the centroid for k-means and k-modes. Okay. And then we also have, just like in k-means, the partition or the cluster update step. And so, just like in k-means, we are going to assign a given observation to its current closest centroid, but we do want to be careful about the distance metric that we're using. So you want to remember in k-means, the distance metric that we end up using, again, is that squared Euclidean distance. Okay. And because we want our distance metrics to be consistent, and more importantly, we want our distance metrics to guarantee convergence to a local minimum, we do want to make sure that our distance metric that we're using for K prototypes is the same one that we use in the corresponding optimization problem. So again, we are going to use that distance metric, which is a combination of the squared Euclidean distance for the numerical variables and the Hamming distance for the categorical variables. And we also end up using that gamma weighting parameter as well. So the gamma parameter weights how much the Hamming distance should be considered in this distance function. Okay. Questions on that? All right. So for instance, we might be curious, or in a particular step, let's just say we have this observation here, and we'd like to determine which prototype it should be assigned to. So we can use that described distance function to first calculate the distance between observation 3 and prototype 1. So that would be 20 minus 2 squared plus 19 minus 27 squared. Okay. And let's just say, for instance, we'd like to use a gamma weighting parameter of 1. We use that here. Okay. And so PhD and masters are different. So we would give a 1 value for that. And then apartment and house are different. So we would also give a 1 value for that attribute here. Okay, so that distance between prototype 1 and observation 3 ends up being 390. Okay, and then we would calculate the distance between prototype 2 and observation 3. So that would be 20 minus 10 squared plus 19 minus 20 squared plus our gamma weighting parameter, which is 1. Okay. And then masters and bachelors are different. There's a disagreement, so we add a 1. And then house and house are the same, so we end up adding a 0. Okay. So when we add all that up, we see that the distance between observation 3 and prototype 2 is 102. So because x3 is closer to prototype 2, we assign x3 to cluster P. All right. Any questions on that? Cool. So what you can see here is that these, prototype-based clustering algorithms end up having a very similar structure to each other. So this should all, be very familiar to you at this point. However, something that we do want to consider is how we might tune this gamma weighting parameter. So in this particular scenario, by using a gamma parameter value of 1, we want to ask ourselves what types of variables were dominating the results of the k-prototype algorithm. Was it the numerical variables or was it the categorical variables? So maybe I'll put up a poll. The 1 says the numerical variables dominated the results. 2 says the categorical variables dominated the results. And 3 says neither. So let me post that really quick. Seems like I've posted an easy question here. Okay, so please try to submit in the next few seconds. All right. So the majority of us say that with a gamma value of 1 in this particular data set, the numerical variables are going to be the ones that end up dominating the results of the k-prototype clustering algorithm. And so based on no other information, not really looking at any potential gaps that might exist in the data set, purely just by looking at, the size of the contribution that the numerical variables are, contributing to this distance function, in comparison to the size of the contribution that the categorical variables are contributing to the overall distance function, we can see that the numerical variables play a much higher role in whatever that distance function ends up, or whatever that distance value ends up being. So because of that, the numerical variables will dominate, most likely dominate the k-prototypes clustering results. Okay, so this gamma parameter can be something that you can play around with. So, for instance, if you want your categorical variables to have more of a say in the results of your k-prototypes clustering algorithm, then you can, try increasing that gamma weight. However, what you might end up seeing, for instance, is that, when your categorical variables have more of a say in the distance function, then what you might end up seeing is perhaps your clustering structure ends up weakening. So you can also play around with this gamma value to determine, what gamma value ends up showing you the strongest clustering structure. So it might be the case that, for instance, like your categorical variables are the main contributors to the clustering structure if you give that gamma value a higher weight. On the other hand, it's possible that your categorical variables do not really significantly contribute to the clustering structure. So in that case, you might consider using a lower gamma weight. And this is, again, if your overall goal is to, find the most significant clustering structure in the data set and then explore it once you've found it. So there's a lot of things that you might consider. We're going to talk about that in the homework assignment. But yeah, any questions on that? Okay. So let's see how we might apply this to our bank data set. Okay. So let's see here. Oh, one other thing that I wanted to discuss, is again, with this TSNE plot that we have created, we can also for instance, explore, what is the relationship between each of our attributes and the clustering structure that is detected by Gowers distance and the t-SNE plot that's created with that Gowers distance matrix. So for instance, we might be able to see that, for instance, there's this relationship between some of the subclusters that exist and the marital status of a person. And there's also this relationship that exists between some of the subclusters and the education level. And we can see, for instance, what type of loan the person has also plays a role into the existence of perhaps some of the main clusters that exist. Now, also the way in which somebody was contacted also, seems to play a role in the existence of the main cluster. So these are all things that you might want to explore, so on and so forth. But so let's focus on using that K prototypes algorithm. So the K prototypes function also comes from the K modes package. So you can find that that function from that package that we've already discussed when we use the K modes function. And again, the K prototypes function is nice because while it's not directly coming from scikit-learn, it very much operates in a very similar way as how the K means function works. So basically, again, you set up all the parameters that you would want to stipulate for that K prototypes function. So let's just say, for instance, we wanted to perform a naive implementation of K prototypes. So simply just looking for, 2 clusters, not really thinking about how we, if that's a sensible number. And again, you want to remember this is a non-deterministic clustering algorithm because we did have that random centroid initialization step. So we should specify a random state. Okay. Now, something that you might notice that I did not do here, but we will do it in the homework assignment, is that I did not specify a gamma parameter. So that can also be an additional parameter that you can specify in the K prototypes function. I'm just going to actually just let the default gamma parameter, I'm just going to use that for now, which is basically 0.5 times the average column standard deviation. But in the homework assignment, we're going to, explore, what different gamma parameters might mean for our analysis. But once we've specified those parameters, we've basically, what we've done here is we've created a K prototypes object. Okay. And then when we're ready, we can actually run the K prototypes algorithm by running fit predict on our mixed data types data set. Okay. Now the only additional thing that you need to specify here is the index of all of your categorical variables in the data set. So the indices of the categorical variables in X. So for instance, let me just grab that here. Yeah, so we can see here, for instance, that the index of age and balance are 0 and 1. So those are our only 2 numerical variables. And then our categorical variables are at indices 2, 3, 4, etc. So we'd want to specify that. Okay. So by using not just the fit function, but the predict function, what that does is 2 things. So it runs the algorithm and it also returns this fit clusters object, which is the cluster labels, basically. Okay, but what we might be interested in exploring first is the prototypes of these two clusters that we've explored. Now, depending on the version of Python that you're using, if you want to extract the prototypes or the centroids, when you use this cluster centroids attribute, the older versions will basically return two separate NumPy arrays, one which basically contains the numerical attributes for your K prototypes, and one that contains the categorical attributes for your K prototypes. I think the newer versions actually just make it a little bit easier for you. They just kind of put it all together. But regardless, what I've done here is I've basically just I've used the concat function to basically concatenate my numerical and categorical variables for each of my two prototypes that I've created here. Okay, so I might be curious in exploring, what do these two prototypes say about the two clusters that I've identified here? So for instance, I can see the ages of the people in these two clusters. They're not all that different from each other. So at the very least, by looking at the two prototypes, we don't really see a strong association between age and the cluster. But what we are seeing, though, is a very large distinction in the bank balance of the people in these two clusters here. And this is also corresponding with the most common type of job for the two people here. So basically the most common job for people in cluster 0 is management. And the most common job for people in cluster 1 is blue collar. And in addition, we're also seeing that the most common education level for people in cluster 1 is tertiary, or like some sort of graduate school. And the most common education level for people in cluster 1 is secondary. So maybe just like bachelor's. So again, we are starting to see this socioeconomic relationship with clusters showing up, just like we saw when we looked at purely just the categorical variables. But again, the prototype or the centroids of the clusters are simply just one set of summary statistics. We're only looking at just one metric that summarizes each of the attributes for each cluster. So we might be interested, like we saw with our K-modes clustering, to explore the relationship between each of the attributes and each of our cluster labels. So that's what we're gonna look at in just a second. But we want to remember that we simply just were using a naive implementation of K prototypes. So we didn't really think too hard about the number of clusters that we should be looking for. So much like we've seen with our other prototype-based clustering algorithms, we can also create a K prototypes elbow plot. And so we can do that by using the cost attribute or our K prototypes object. And so basically what this cost attribute returns is the objective function value, or basically the value of the function that we are ultimately trying to minimize in the K prototypes optimization problem. Or in other words, it's the sum of the distances of each object to its cluster prototype. And you want to remember that that distance that we're using is the weighted combination of the squared Euclidean distance and the Hamming distance. Okay. All right, so we're going to use that to cluster our data set as we've seen before. Each time looking for, one cluster, 2 clusters, 3 clusters, 4 clusters, so on and so forth with the K prototypes algorithm. And we're going to plot that resulting cost on our y-axis. Okay. And we can interpret the corresponding K prototypes elbow plot to, again, determine, is there a clustering structure that at the very least, K prototypes is able to detect. And again, that's based on how strong of an elbow you see. And if you do see an elbow, that can also give you an indication as to the number of clusters that at the very least K prototypes is able to detect. Okay, so in this K prototypes elbow plot here, it's it's not very clear. Maybe you could go with 2 clusters, maybe you could go with 3 clusters. We are seeing a slight elbow showing up here, so indicating that at the very least, K prototypes with this particular gamma value is detecting a slight clustering structure. So in a scenario such as this, in which it's not necessarily clear what the most distinct or the most leveling off point is, you could in fact choose to explore both cluster numbers. So, create a clustering with 2 clusters, create a clustering with 3 clusters, and see what kind of results that you get. But in the interest of time, we're just going to keep exploring that K prototypes clustering with 2 clusters, which is what we do here. Okay. And so what we might do, and this is something that we have done with a lot of our clustering algorithms, again, nobody's ever going to really tell us don't use k-means, don't use K prototypes, don't use this particular clustering algorithm. But usually, right, what we hope is the case is that if we're choosing to return a certain set of clusters, generally what we're implying is that, hopefully there does exist some sort of meaningful separation that exists between the 2 or however many clusters that we've returned. Otherwise, it's possible that we might be a little bit misleading with the results that we're returning. So we've been getting into this practice of using the TS&E plot to help us corroborate whether there actually exists this meaningful separation between the clusters that we found with an actual clustering algorithm. So we did that here. So we plotted our K prototypes our K prototypes cluster labels. We color coded by those labels, and we overlaid them on our TS&E plot, or a representative TS&E plot that we chose. Okay. And so the question is, what we're seeing here, right, is there's a fairly even distribution of 0 and 1 cluster labels amongst the the clusters suggested by the TS&E plot. So this indicates to us there's really not a strong association between the TS&E plot suggested clusters and the K prototype based clusters. So at the very least, this particular TS&E plot is really not giving us a strong indication yet that there actually does exist this meaningful separation between cluster 0 and cluster 1 that our K prototypes found. But the question is, at this point, should we expect to see a strong association between the TS&E, or what the TS&E plot is suggesting about the clustering structure, and what K prototypes is suggesting about the clustering structure? So I'm going to ask a poll here. No, hold on one second. Here's the question. Should we expect, even in the best of scenarios, to see a strong association between what TS&E is saying about the clustering structure and what K prototypes is saying about the clustering structure? And if not, why? So start typing it up in the chat. Okay, so try to submit in the next few seconds. So I'm curious what your intuitions are here. Okay. Okay, so the majority of us say no, and I say no as well. So why should we not expect necessarily to see a strong association between what the TS&E plot is saying about the clustering structure and what K prototypes is identifying about in the clustering structure? Cluster 0 doesn't form any clusters in the TS&E. Yeah, well, so I mean, this is just a particular instance of us using K prototypes um, to cluster a given data set and TS&E to reflect the clustering structure of a given data set. So what I'm talking about is in general. So like for any data set in which we were to basically use K prototypes and use the TS&E, would we expect any data set necessarily to have a strong association? Yeah, exactly. So I'm seeing so what you want to remember is that we're actually not necessarily creating an apples to apples comparison, or we're not creating a consistent comparison of the clustering structure, because you want to remember the distance metric that we're using to create the TS&E plot is the Gowers distance. And then the distance metric that we're using in K prototypes is different. It's that combination of the squared Euclidean distance and the weighted Hamming distance. So you want to remember that. So the distance functions that we're using to detect clusters in these two algorithms is not the same. So in the TS&E plot, we used Gowers distance. And in K prototypes, we used the weighted combination of the squared Euclidean distance and Hamming distance. Okay, so this is not a fair comparison to make. So therefore, this particular TS&E plot may not as accurately reflect whether or not there exists meaningful separation between the K prototypes clusters using the same distance metric that K prototypes used. So in other words, what we're saying here is that it could actually still be possible that there is in fact some sort of meaningful separation that exists between K prototypes clusters 0 and 1. But because we weren't actually using that same distance metric that K prototypes was using, this particular TS&E plot is not necessarily going to be able to, reflect that meaningful separation that might exist using the same distance metric. So a better TS&E plot to have used to better help us evaluate, whether these K prototype clusters are in fact meaningful is one in which we created a distance matrix originally that matched with the same distance function that we were using for K prototypes. So we'll talk about doing that in the homework assignment, essentially. But you want to make sure that, when you're actually using these TS&E plots to help you further evaluate a given clustering that you found somewhere else, you want to make sure that the distance metrics that you're using are in fact the same. Okay. All right, questions on that? All right. So I'm going to do a little bit of post-cluster analysis. So we've seen this before with K-modes. So for instance, you could explore the relationship between your two cluster labels and each of your categorical attributes by using a side-by-side bar plot visualization. And so, for instance, we end up seeing a lot of the same, you know, the same insights that we saw with, when we use K-means. So, for instance, we see that cluster zero is comprised mostly of, people that work in management, or it has a much higher proportion of people that work in management. On the other hand, cluster one is comprised of a much higher proportion of people that work in blue collar jobs, so on and so forth. Okay, so it's 4:30, so I'm going to take a quick pause. So I'll let you guys check your email. Okay. Okay, so I do see that both of my sets of emails have gone out. Okay, so I'll give you about 30 seconds just to check your emails and ask me any questions that you might have. But again, if you've been selected and you encounter any problems, Jordan is standing by to help you answer any of those questions that you might have. Okay. All right, so I'm going to assume that everybody has checked their email, and for those of you who have been selected, good luck. This is not, don't sweat it. As long as you understood something about what you put on that page when you submit your homework assignment, you should be good to go. Okay, so I'm going to assume that everyone that is still here was not selected. So we are gonna keep going. Yeah, to be honest, I'm not sure why some people are not getting these emails. It's very, very perplexing. Let me just double check this here. Let's see. And I would say if you don't see your emails showing up, check your junk mail. Now, it is possible that, for instance, it might take a little bit of time for some people to receive the email. Like, for some people, for whatever reason, it might not go out right away. But yeah, let me just respond. Just one private message that I'm getting here. Okay. All right. So I'm going to assume that everybody has, everyone else, nobody who's messaged me is confused about whether or not you got the email. So we are going to proceed. So just to wrap a couple things up. So for instance, you can look at the relationship between each of our K-prototype cluster labels and each of the categorical attributes. But because we also had some numerical attributes, we can also explore the relationship between each of our cluster labels and the numerical attributes. So we can use the same side-by-side box plot visualizations that we used when exploring K-means clusters. So for instance, we can see here, because there's not a strong association between age and predicted cluster, essentially what that's telling us is that age is not strongly associated with the clustering relationship here. Or in other words, because there does not exist, any separation between the IQR boxes, there's not a strong association between, the clustering structure and age. On the other hand, though, we do see a very strong separation between the IQR boxes for the bank balances for the people in these two clusters here. So we are starting to see more of this socioeconomic breakdown, again, in a more nuanced setting in which, basically everybody in cluster zero has a very small bank balance, but a lot of people in cluster zero have a much higher bank balance. And so these are all the people that, like worked in management, and these are all the people that worked in more blue collar jobs. So we are seeing that, again, that socioeconomic status breakdown. Okay. All right. So that's how you would use K prototypes to learn about or basically to create a single partition based cluster of this mixed data types data set. Any questions on that? Okay, so finally, to wrap things up, when we were dealing with a purely categorical variable data set, if we wanted to explore potential nested subcluster relationships, which our TSNE plot suggests, might exist. We talked about how to create first a Hamming distance matrix of our categorical variable observations, and then basically use that Hamming distance matrix as input into our hierarchical agglomerative clustering algorithms. So we're going to do a similar thing for our mixed data types data set. So first, we're going to use our Gowers distance matrix, and then we're going to use that as input into our 3 hierarchical agglomerative clustering algorithms using single linkage, average linkage, and complete linkage. So we've already created this Gowers distance matrix before. Okay, we want to remember the Gowers distance automatically returns a distance matrix which is in square form. But what we want to remember is that when we create our dendrograms, the actual type of distance matrix input that we actually need is one in which that distance matrix has been flattened. So basically we take this and flatten it into a one-dimensional array. So if we ever want to flatten a square form distance matrix, we can still use the square form function, but then we use this force to vector parameter to basically flatten it, essentially. So that creates this slightly different version of our Gowers distance matrix here. Okay. And so basically, once we have our flattened distance matrix, the way that we create our dendrograms with that Gowers distance matrix is exactly the same. So for instance, I might use single linkage to create my single linkage dendrogram. Okay, so it creates this linkage function object here. Ooh, I am running out of breath. And so again, we use that linkage function object with our dendrogram function. And again, I'd like to, because there's so many observations in this data set, I would like to truncate the dendrogram such that I'm only looking at the final 200 merges, and I don't want to see the labels either. Okay. All right. Whew. And so this is the dendrogram that we actually end up getting when using single linkage. Okay. So what do we think? Just based on this dendrogram that we're looking at here, looking at nothing else like the TSNE plots, do we think that this dendrogram is actually going to be able to help us identify meaningful main or larger clusters in the data set? So that's the question. I like how somebody said no before I finished the question. Okay, yeah, so most of us say no. Yeah, and that is going to be the case. And we often end up seeing this in the case of single linkage, in which, if we end up having any prominent outliers, or even, outliers that are not even all that far away, what the single linkage dendrogram will end up returning is a series of singleton clusters that iteratively get picked off one at a time as we move down the tree. Now, again, because we truncated this dendrogram, it's possible that, this observation here, basically this, this branch doesn't actually necessarily just represent one observation. It could technically represent multiple observations. But if we use, for instance, our TSNE plots, and color code our resulting partition-based clusterings found in that dendrogram with 2 clusters, 3 clusters, 4 clusters, so on and so forth. We do end up seeing that, that is what is going on. We end up picking off a singleton outlier here, a singleton outlier here, so on and so forth. Okay, and if we just keep going down the line, we never, end up finding a clustering, with a large amount of observations. So we never end up finding one of these larger main clusters that the TSNE plot suggests might in fact exist. But, the nice thing is if you were looking for a technique that helped you identify an outlier in your mixed data type data set, then this single linkage dendrogram could in fact end up proving useful. So for instance, it might be the case perhaps in some of the clustering algorithms that we end up using that the existence of outliers could impact the performance of your algorithm. So this dendrogram, for instance, would give you an indication that there are in fact these observations which have a very far away Gowers distance from their nearest neighbor, essentially. So for instance, you might consider perhaps filtering out some of these observations that have a far away Gowers distance between them and their closest neighbor, if you will. However, our main goal here is to, identify large clusters of people. We don't want any singleton clusters in this particular analysis. So it doesn't seem like single linkage was all that helpful. So what we might do instead is move on to complete linkage, which, as we've discussed in our hierarchical collaborative clustering unit, is not as sensitive to the existence of noise and outliers. So in other words, if in fact your data set does have outliers, the clusterings that complete linkage returns are not going to be, or they're less likely to be comprised of these small singleton outliers. But we want to remember, complete linkage, as with any of our clustering algorithms, also has its downsides for particular types of data sets. So what is one of the downsides of complete linkage? So, yeah, exactly. So it tends to separate large clusters. And so the nice thing about our TSNE plots is that they can actually give us an indication sometimes as to whether or not that actually happened. So let's see if that happened here. Okay, so I use complete linkage with my Gowers distance matrix now, and I do see that, yeah, I am getting some evidence that the first or the final few clusters that were merged, or conversely, the first few clusters that were split as we move down the tree are not these singleton outlier clusters. But I can get further corroboration of that by, again, color coding, excuse me, my clusters in my TSNE plot. So this is the clustering with 2 clusters. This is the complete linkage clustering with 3 clusters, so on and so forth. Okay. And so what I'm seeing here is, as I go down the line, looking for more and more clusterings, I'm definitely seeing more well-balanced clusters. But again, what would be ideal is for me to have this additional layer of corroboration that the clusters that I'm separating in the complete linkage hierarchical agglomerative clustering algorithm do in fact actually have this meaningful separation that exists between them. Or in other words, I'm not just taking a blob of points and splitting it up. So here we can see also in our TSNE plots that, again, we're not really seeing this strong association, or not a very strong association between the clusters suggested by complete linkage hierarchical agglomerative clustering and the clusters suggested by the TSNE plot. So in other words, what that might suggest to me, for instance, is that, there is not necessarily going to be this meaningful separation that exists between cluster cluster 0 and cluster 3, for instance. So, what this is suggesting to me perhaps is that, by creating cluster 0 and cluster 3, we might just be cutting up a blob meaninglessly. Now we saw that when we saw that same relationship to some extent when we clustered the data set by using K prototypes, right? But we wanted to we took that interpretation with a little bit of a grain of salt, right? Because we said, well, okay, K prototypes was using one particular distance function. The TS&E plot that we were using was using a different type of distance function. So we want to ask ourselves, in this scenario, are we actually using the same distance function for hierarchical agglomerative clustering and for the TS&E plot that we're looking at here? And so I'm talking about the original distance metric or the original distance matrix that was used as input for these two separate algorithms. Okay, so try to submit in the next few seconds. Okay, so I'm seeing slight majority of people saying yes. And so, yeah, we are in fact now using the same distance matrix as input for the TS&E algorithm that created this plot and the hierarchical agglomerative clustering algorithm that created these clusters here. So the answer is yes, they both now use Gowers distance matrices as input into the algorithms. So because of that, we can trust that the TS&E plot provides more of an indication as to whether the cluster or the hierarchical agglomerative clustering clusters are in fact meaningfully separated or not using the same distance metric to measure separation. Okay. So what this is indicating to me is that because now we're using the same distance metric, this is now providing an indication that perhaps complete linkage is in fact, cutting up these large clusters, if you will. It's taking, for instance, this pink cluster here, and it's cutting it up into cluster 0 and cluster 3 in a non-meaningful way. Or in other words, there's not necessarily a meaningful separation that should exist or that does exist between the observations in cluster 0 and cluster 3. Okay, so we saw some downsides with single linkage, which was sensitive to the noise and outliers, and we saw some downsides to using complete linkage, which again we see is sensitive to splitting up large clusters. So what we saw, when talking about hierarchical agglomerative clustering, is that average linkage tends to strike this middle ground between the pros and the cons of single and complete linkage. So let's see if using average linkage can help solve these two problems that we're experiencing here. So let's use average linkage. So all this code is the same. Okay. And so we can see our dendrogram. I know I'm running out of time. If we look at the first two clusters that are split as we move down the tree, unfortunately, yeah, one of those clusters is not very big. So it might indicate perhaps we are going to start seeing some of that noise and outlier sensitivity that we see with single linkage. But let's color code some of those average linkage clusters that we ended up getting in that dendrogram. Okay, so we can see that as we look at, some of the first few clusterings that are created as we move down the tree, we are getting sort of this, picking off effect of, small subclusters from the main, larger set of observations. But eventually, as we get to the clustering with 7 clusters, we do end up seeing this separation of cluster 2 and 1, in which the TSNE plot does provide this extra layer of corroboration, and that there is actually this meaningful separation between that cluster 1 and that cluster 2. So this further, builds corroboration that, this particular clustering, particularly cluster 2 and 1, does in fact have this meaningful separation. So we're not simply just cutting up a blob of points. On the other hand, the downside, though, is in order to get to that clustering, we had to pick off a bunch of, small subclusters, if you will, and then we need to think about, well, what do we want to do with all those other clusters? Okay, and furthermore, as we keep moving down the line, we do end up seeing this further, separation of clusters that do have this, association with what the TSNE plot is suggesting. So this is further, providing additional corroboration that, cluster 1 and cluster 0 that was created here are in fact meaningfully separated. So there is more of a meaningfulness to the clustering that we're creating here. It's, we have more trust that there is in fact this separation that exists. So anyways, there's pros and cons of all of the different clustering algorithms that we discussed here. But yeah, based on your particular research goals, you would want to evaluate those pros and cons. And yeah, think about what the best solution is for your needs. Okay, so that basically wraps up with Unit 6. We've now talked about how to cluster numerical data sets, how to cluster categorical data sets, and how to cluster mixed data type data sets. And so, yeah, you basically have all the tools that you need to assess whether a given data set is clusterable. So I would say that's, if you want to start looking at data sets that you find interesting, have at it. Okay, cool. So I've gone over, so I will stop recording.